now we will go right on to integrating the equation that we derived last lesson. Okay. What I'm gonna do is actually to explain what the hell we are doing just now. Okay. So first we actually at the very first part we talk about Navier-Stokes, and then we say that this is the equation that can represent the x direction, and this is the equation that can represent the y direction, and this is the equation that can represent the z direction, right? And then we have a question that tells us that dude, we're gonna find the velocity component in the u direction. So this is why we straight away use this equation, because it's only in terms of the x direction only. Okay, and then we also put in certain parameters. We say that steady state doesn't change with time, cancel, and then incompressible density cancel. Okay, and then we talk about 2D flow, so the z is cancel, and then this z is also cancel. Okay, and then since 2D flow and assume that v is negligible, so the y direction is negligible also, we are only left with x direction, so this is also cancel. Okay, however, we didn't cancel this portion over here, because this portion over here contributes to a certain stress. Okay, so the reason why we cancel away z direction, this is the part I can't understand. Perhaps you say that assume that this is only 2D flow. So 2D flow, there will be no z components contributing to the stresses, but still there will be y component contributing to the stress. This is what it says, right? That's what I mean. And therefore we know all these parameters and assumptions. Really, we cancel here and there. We are left with this portion over here, and then what I mean is, so we say we cancel all the stuffs, right? We cancel all the stuffs, and then we have this equation over here. So this is just a leftover. We just bring it over here, and then the rest we just bring it over here. This is what I mean, right? So this is the very first part, setting our parameters. And then the second part is to actually average velocity. It's a very important keynote you need to take note. It's the constant average velocity. Okay, so the constant average velocity comes when you have fully developed. Okay, fully developed is when your shaft is spinning in a constant velocity. Okay, so when it is steady spinning and happily, okay, you have fully developed. So this velocity and this velocity is always the same throughout the whole system unless you stop the machine. Then you start to slow down, and there will be no velocity profile anymore. So this is the velocity profile, right? And therefore, since we say that this is steady, since we say that this is fully developed, then we can say that this thing can no longer change with time, because it is always the same throughout. So we can actually average them into this. We just add this layer together, add all these layers together and divide it throughout y, and you can get this straight line constant. And with this, then we say that in the x direction there will be no variation anymore, because at first there will be x variation, right? This is different from this portion, is different from this is different from this, right? So since we have constant average velocity, it is always constant. And then we can clear away all the x that is contributing to whatever it is. So we can cancel this, and this. We say that because these are all variated with x, right? We variated with x. But since you are taking average now, the x's, this x are no longer being looked at. Okay, but you may wonder why we didn't cancel this also, because this is pressure gradient. Pressure gradient will nonetheless change. Okay, there may be certain pressure gradient still, although this is constant, right? There is still in the Bernoulli's equation, if you remember. I don't know, did I put it over here? Hold on. If you remember the Bernoulli's equation, we have something with the plus rho gh, right? So there will be still certain pressure gradient across the height. although we say that this is negligible, right? But we didn't put it into our assumption that this is negligible, right? So this, in certain sense, there will be a certain pressure gradient along the thing. So therefore, since this is since these and these are constants already, because velocity don't change, pressure is always the same. So only changes is only the pressure gradient is always with this, right? And then this constant is actually the total pressure. Okay, this is actually the, if I know, this is the dynamic pressure. Is when it's moving, there is a certain pressure. I think only. Okay, so nonetheless, this is it. So this is only, I may be wrong throughout the whole stuff. Okay, I may be wrong in explaining this term over here. Pressure gradient is due to the leftover of this rho GH over here. I may be wrong, but yeah. So nonetheless, we derive that we have this term. And let's bring over here. I just bring it over here so it becomes plus. So it's positive, and then I just bring this down together with this. So and then I just bring this nu over here, and then we have this equation over here. So with this said, questions tell us to derive a horizontal velocity component u. So since you can see, the reason why I bring this u over here is actually to make it, in terms of u and y, so we can differentiate. I mean integrate, sorry, because the only term over here is actually u. The only u over here is only this portion over here, so we can just integrate. So you integrate 2 times. In this case, just remember again, for num-pipe system, okay, num-pipe in our case is the shaft and the thing, right? The bearing, the engine shaft, okay. Okay, this is I don't know what the hell, but this is the bearing, okay, and then the shaft is on top of this, and then it turns, right? I don't know whether you do visualize it, okay, but anyway, so this is the engine shaft, and just now I just talked about this is the bearing, right? So this piece is the bearing, so this piece is half of the bearing, and then you cap onto it, and then you have a shaft spinning on it. So yeah, what am I talking about? To find the velocity u, we integrate 1 time. So this is the integration. We integrate in terms of y. Okay, why do you integrate in terms of y, right? Because the u, okay, the u itself, this is the u, right? And this is the velocity of the plate u. The u varies along y, right? As y increases, there is a certain variation, but now in this case, there is no variation at all, constant. But we can still integrate because, yeah, we're trying to find u. Okay, we're trying to find u. So you integrate 1 time, you get a constant c over here, right? And then you integrate again. Okay, you have you just plus 1y over here, and then plus d. It's just simple, not simple, but rather than okay lah. That's like integration. That's all. So you integrate 2 times. You apply your 2 boundary conditions. The boundary conditions you need to know. Okay, is simply when y is equals to 0, what happened? When y equals to a, what happened? So this is just at the top of the plate and the bottom of the plate. So when y is equals to 0 and y equals to a. So at y equals to 0, the velocity here should be 0, right? Now we are talking about this. We are coming back here again. Okay? That's why it's a little complicated here and there. So you just need to know how to do. Okay? So let me repeat again. When y is equals to 0, the velocity here is 0, right? The u 0. And then y is equals to a, the uy is equals to u. That's the velocity of the plate. Okay, the velocity of the shaft turning. Right? So therefore, we can actually apply the 2 boundary condition. And next video we'll talk about it. And then yeah, so I'll just stop here. And then next video we'll apply the 2 boundary conditions as. So see you in the next video.